Good evening, everyone. Let us get started with today's discussion, which is first I'll summarize whatever we have discussed last day. So, last day in the last class, we discussed about several numerical methods and also saw their impacts on the simulation. So, here is a summary of that. Like, if any system we have differential equation, we have dx dt equal to fx, then this equation will be approximated or expressed in difference equation format. Yeah, if we use has to be expressed in difference equation format using some numerical method, which are nothing but numerical integration methods. So using forward Euler as shown graphically here, this is kth instant, this is k plus 1th instant. So the left hand side is always expressed like this: xk plus 1 minus xk divided by h, where h is the time step, time duration between k1 tk plus 1 and tk. And basically what we have to do, we have to approximate this exact integration by some approximate terms. So we have to integrate fx from tk to tk plus 1. So how do we approximate that? Based on that, there are several numerical methods defined. So first one is forward Euler, where the present instant value of fx will be carried forward and will be assumed to be the value of fx for the h duration. So in that case, the integration of fx from tk to tk plus 1 will be nothing but the blue hatched area, which is h. H is the horizontal one and fxk is the vertical one. So this is the integration value. Now if we have to do using backward Euler, then backward Euler, the future instant, so k plus 1th instant value of fx will be carried backward during the or for the during this h interval. And so in this case the horizontal distance remains the same, that is h, and the vertical distance is the red one, that is f of xk plus 1. And so the integration value output will be h into f of k plus 1. But neither of them is very close to the actual integration value, because actual integration value is what is the area under the black curve, which is shown here. So the black curve is the exact fx curve. So the area under this is actually the black hatched area that I just indicated. But you can see that the red area as well as the blue area, as approximated by the forward Euler or backward Euler methods, they have certain errors, and the error can be minimized by actually taking an average of the two, that is approximating the fx with the green one, which is nothing but the average of the fx k and fx k plus 1. So in this case the integration output will be the green hatched one. So h, this is the horizontal distance, and the vertical distance is half of fxk and fk plus x plus xk k plus 1. So these are expressed in these equations also. So these are three basic numerical methods, among which the first one is explicit. So on the left hand side and right hand side, only left hand side you have k plus 1 terms. But backward Euler and trapezoidal, they are implicit methods. Why implicit? Because k plus 1 instant value actually exists on both sides of the equation. Similar thing is true for the trapezoidal as well as trapezoidal method also. Here also left hand side, right hand side, both cases you have k plus 1th instant values or quantities. Now we looked at the field voltage field equation, and if that is actually expressed in state space form, this will be dif as shown in the with the box is equal to minus k1 if plus k2 vf. Now if This is to be expressed using the forward Euler. We derived, this is the equation. Backward Euler, this is the equation. Trapezoidal, this is the equation. Now the question is how to choose, or uh, which method to choose where, and how to choose the time step h, and what is the impact of the time step on the solution. So the basic thing is we have some system, we are approximating the system differential equations using one of these methods, say forward Euler, backward Euler, trapezoidal. One thing is it has to be accurate, but furthermore, which is more important, is the system output or the system response should be similar to the continuous time system response. It should not be dramatically different, or it should not go into instability. So we will see that actually numerical, even if our system is stable, because of improper choice of numerical methods or the time step h, the stable system may act as unstable in certain cases because of or because of improper choice of numerical methods and improper choice of the time step h. So let us start. So for getting the basic understanding, let us first define what do we mean by stability of a system. First, let us define the stability of a continuous time continuous time system, and from there, from those understanding, we will extend that to understanding stability because of numerical methods, and from there we will understand what is the correct numerical method for a given system, and what is the correct time step to be chosen, and what are the implications of time step in many cases. So what do we mean by stability? So a system, any system will be said to be stable if the response remains well behaved. So if the response is well behaved after it is subjected to some disturbance or some change in input. So what is stability? A system can be said to be stable if its response, so the response is well behaved when it is subjected to some disturbance or some change in input. What is the meaning of that? Suppose the current, let us take the case of a field winding circuit. So we have the current is one of the state variables of the system. So the current, let us say current, this is if, this is time. So let us say time is current has reached steady state and it is at one of the operating points, which is the some DC value of current. Now if we suddenly give some change in the DC voltage, like there is a field voltage, will the system come back, or will the current value change abruptly and go to some very high value, or very high value, and it will not stabilize at all? So it may happen that it keeps on oscillating, or it goes to very high values, then the system will be told to be unstable. But if the current actually either increases and then stabilizes to another steady value, or it may oscillate for some time and then eventually settle at some other value. It may increase, decrease based on the disturbance and input that you are giving, but whether the response is well behaved and whether it is settling at the new steady state value, or it is actually going to instability because of the disturbance or the change in input. That is the definition of stability of a system. Now here I have used a very subjective term, well behaved. Many people may define this what is meant by well behavior differently. So based on that, there are different definitions of stability, but just to give one very crude example that is given for in all textbooks as well as in all discussions, let us take some examples of stable system, then unstable system, and a marginally stable system. So stable system is like, say you have a U-shaped wall based on something, and you have a ball, and in steady state or after all disturbances are gone, the ball lies at this location. Now if you give a small disturbance in the ball, like you push it on one of the sides, what will happen? It will keep on rolling, and after some time, if the system has if the surface has certain friction, then eventually it will come back and again become steady at the same position. So even if we are disturbing the position of the ball, where eventually it comes and becomes steady at the same of a steady operating point. What is the meaning of unstable system? What is the example of an unstable system? Only you make the U reverse U, and you keep a ball, right? The ball may stay here, but if you give even a small disturbance to the position of the ball, it will simply go and keep on rolling, and it will never come back to the original position. So this is an unstable system. What is the marginally stable system? Marginally stable system may be the same example what I have taken here in the first case. The same example might be taken, and instead of, this is a friction with a surface with friction, but say it is a smooth surface without any friction. So in this case, if the ball may be staying here only, if you give a small disturbance, because there is no friction, so assume that there is no air friction, there is no surface to surface friction also, then if you give some push, then it will keep on oscillating, keep on going forward and backward, and it will keep on moving here only. So it will, although it will not become unstable, but it will remain, it will not come back to the stable position also. So it is an example of marginally stable system. Or another example can be given, say you have a smooth surface with some and you have a ball, and if you give a small disturbance, after some time, so the ball moves from here but comes back to some other new position and keep and stay there. So this is where you are so your steady state or the equilibrium position is actually changing, so it can also be defined as the marginally stable system, because it does not come back to the original stable operating point. But yeah, in this case there can be, so all points are basically equilibrium points. So in that sense, the first example that I have given, that is a more that is a better example of a marginally stable system, where because of a small disturbance it keeps on oscillating. So that is also the case of a pendulum, a simple ideal frictionless pendulum. If you push it to one side, it will keep on oscillating. So that is also a marginally stable system. Now, as I have told that the definition, that whether so what do we mean by well behaved? Is there a way to define that? So there are different definitions of what is meant by well behavior or good behavior for a system to be called as stable. So first of all, we have to understand what is meant by equilibrium point. So equilibrium point means if any system has certain input, and then only it will give some output, and internally it will have some state variables. So with zero input, if the output or the state variables remain always steady there, and even if small disturbance is given, it will always come back to the same point. That point is called as the equilibrium point. So generally, if you have a system, say a very simple system, say x dot equal to fx. Now if you have to put the time derivative of x to be 0, you have to put x dot equal to 0, and by putting that, whatever value of x, say e, you will be able to solve. That is the equilibrium point of the system. So this is equilibrium point. So what is the meaning of that? With 0 input, system stays there, and some small disturbance, system comes back to the same steady state equilibrium point. Now the first and most uh, say the first and most simplest example of or definition of stability was given by Lyapunov. So what is that? It is mostly a mathematical definition and applicable for all dynamic systems, but specifically it is used for nonlinear systems, although it is valid for linear system also, but we will see that for linear systems there are actually more better definitions of stability, but nonlinear system, this definition is very very well used. It is widely used to define stability. So all systems will have some state variables. So say a state variable has some, say state variable is x, and it has some equilibrium point, say xe. Now x, the initial condition, so x at 0 is equal to x0, which is sufficiently close to xe, that is it starts very close to xe itself, and if it is given some disturbance, a small disturbance, then xt, like x will change with time, but xt will always remain very close to equilibrium. It is not explicitly told that it will come back to the equilibrium point, but the definition tells that it remains reasonably close to the equilibrium point for all future time. So if you give a small disturbance, it remains stable. So an example can be, say, because it is mostly used for nonlinear system, I will take the case of a pendulum only, and I will not simplify the pendulum equation. So this is pendulum, and the differential equation is like, if this is theta, then what is the differential equation you have? You have x double dot, which is nothing but the double derivative of theta with time, that is equal to, or that plus sine theta is equal to 0. So this is the exact dynamic equation of a pendulum, where which is a nonlinear system, because you have some sine of theta. You simply do not have a linear function of theta, but it is a sine of theta. So it's a nonlinear system, and in this case, what is the equilibrium point? Steady state equilibrium point is this, and say without any input, it or with a small disturbance, say it starts from some other point which is sufficiently close to the equilibrium point. If it starts from there, it will keep on oscillating if it is a pendulum with no friction. So if it is, even if there is a very small displacement from the equilibrium point, it will keep on oscillating. It will not go very far from the equilibrium point, but it will not go and stabilize at the equilibrium point also. So this is an example of a nonlinear system where the system is Lyapunov stable. Now let us go to the next example, next definition of stability, which is which is the one which we will be using subsequently also, and it is very widely used for linear systems. So what is the only difference from here? Here we told that even if there is some initial condition which is away, which is not exactly equal to the equilibrium point, it will always remain sufficiently close to the equilibrium point. It will not simply go out of very far from the equilibrium point. But this definition of asymptotic stability says that the state variable or state variables, if a system has multiple states, so this is x. Now it says that xt will tend to 0 as time tends to infinity. So as any system, if there is some small disturbance, so what I am assuming here is the steady state equilibrium point for the state is basically 0. So that is, or more exact, it will be some equilibrium point. X tends to the equilibrium point as t tends to infinity. In this case I have taken 0 as the equilibrium point, so that is why I have written xt tends to 0 and t tends to infinity. So what is the difference from the previous definition? Previous definition says that it will be reasonably close to the equilibrium point, but this definition tells that it has to eventually go to the equilibrium point. If it is 0, then it has to go to 0 as t tends to infinity. If it is some other point, say xe, it has to go to the xc operating point. Now let us take an example of a system which is asymptotically stable. Say x dot equal to minus x. It's a very simple system. Now first let us try to get the equilibrium point. To get the equilibrium point, we need to put x dot equal to 0. So it becomes minus xc. So we get xc equal to 0. So 0 is the equilibrium point. Now if we solve for this differential equation, I am not solving it explicitly here, but the solution will be like, it will be this: x of t is equal to x0 e to the power minus t, where x0 is the value, or x at x of 0 is equal to x0. This is the initial condition of the state variable. So graphically, if a system has a state variable, say x of t, how it varies with time, if without any input, say if it has some initial condition, say x0, basically this equation tells that it comes back to 0 exponentially. As t tends to 0, it will eventually come back to 0. So this is the graphical representation of the system response, and we can see that it is actually dying down to the equilibrium point, that is 0. So that is why it is asymptotically stable. Now there is another definition of stability which is called as exponential stability. So from the last one just told that it has to come back to 0, right? It has to come back to 0, but how long should it take to come back to 0 or the equilibrium point? The stability definition keeps mum about that. It does not tell anything about that. But the next definition of stability also explicitly tells that. It tells that, say a state variable is there, a state variable xt is there, it has some initial condition, say x0, and it has to come back to 0. It has to come back to 0, right? That is a given. But it has to come back to 0 at least as fast as an exponential delay. So what is exponential delay? It is basically e to the power minus some k into t, where a k can be as small integer, any real number, it can be any number as small as possible. But so it has to be at least as fast as an exponential. So you could take a small number as small as possible of k. So the system has to be at least as fast as that to come back to 0. Then it is called exponentially stable. So the mathematical definition goes like this. So if it is xt, it has to be always less than equal to some say some m e to the power minus alpha t into x of 0. So this is an exponential function. You can take alpha to be as small as possible, but xt should be less than equal to that. Xt should not be greater. Xt should not take higher time to reach to 0 from a equilibrium from an initial condition of x0. So this one, this is this equation clearly tells you that this is asymptotically stable as well as exponentially stable, because the state variable comes back to 0 exponentially, so it is exponentially stable. Now let me give you an example of a system which is asymptotically stable but not exponentially stable. So let us say x dot equal to minus x cube, right? So by putting first letter, we have to get the equilibrium point x dot equal to 0. So we get 0 equal to minus xc cube. So basically means xc equal to 0. So in this case also 0 is the equilibrium point. Now if we actually solve that, dx dt is equal to minus x cube. If we solve for this, the solution will eventually come to be something. I am just writing it from the solution that I have. If x0 is the steady state operating point, it will be something like 1 plus yes. So this is the solution. This is the solution of the system. If you simply do variable separation and solve this, and then you use the equilibrium point and the initial condition, you can get this solution. Hopefully there is no error in that. And so what is this? So you can see that as t, if I go to very high time, if t is very high, then 1 plus 2x0 square into t can be approximated. So in this case, if time is very high, t is very big, then this can be approximated as only 2x square into t, right? This one will be negligible compared to that. Then this will become like x0 divided by 2 into x0 square into t, which will be so x0 will get cancelled, so it will be 1 by root 2 into under root of t. So this is, so the solution for t very greater than 0, this basically becomes t to the power minus half, right? This is a polynomial which also as t tends to infinity actually goes to 0, but this is not exponential, this is actually slower than the exponential. So that is why this system as described by this is not exponentially stable, but actually it is asymptotically stable. Right, now let us go to some marginal stability definition. It is simply the same system that I have already discussed. It's a pendulum system with, so pendulum system, the exact equation is x dot plus sine theta is equal to 0, where theta is nothing but this angle. But if this theta is sufficiently small, if this theta is very small, for very small values of theta, sin theta is actually close to can be approximated as theta. So for very small values of theta, sin theta can be approximated as theta. That can be seen if you do the Taylor series expansion of sin theta, then you will find that sin theta is actually theta minus x cube by factorial 3 plus x to the power 5 by factorial 5, etc., etc. So for very low values of theta, you can see that all these higher order terms can be neglected and sin theta can be approximated by theta. So this, for if we apply the approximation of theta being very small, then this becomes theta double dot plus theta equal to 0. So if it is solved, then you will find that theta, as it varies with time, will actually be a sinusoidal function. It will be some a cos of t plus b sine of t, right. There will be this is a sinusoidal function. That means it will theta will keep on varying sinusoidally. So if we start from some if this is given a small disturbance, then it will keep on oscillating if it is a frictionless system. So it is also an example of marginal stability. Now just to um, uh, tell about the difference between marginal stability and Lyapunov stability. Both are, so Lyapunov stability is mostly used for nonlinear systems, whereas marginal stability is mostly the term marginal stability only is mostly used for linear time invariant systems, which will be mostly dealing with. So yes, and just to make another point, this exponential stability and asymptotic stability, they are same for linear systems. If a system is linear, then if the system is asymptotically stable, it is also exponentially stable, and vice versa. If it is exponentially stable, it is asymptotically stable also. So the difference only comes for nonlinear systems. Nonlinear systems, it might be asymptotically stable, but it may not be exponentially stable. But anything which is asymptotically stable, or sorry, if anything is exponentially stable, it will be asymptotically stable also, because exponential stability just adds a new criteria, that how fast it comes back to the equilibrium point. That's all. So next is instability. Again, you understood from the previous example that if a small disturbance is given and it produces very large deviations from the equilibrium point, then it is an unstable system. Example can be x dot equal to x, right. So if it is solved, then xt will be x0 into e to the power t. Then it will look like this: xt as a function of time. Say if it is the initial point x0, then it will exponentially grow with time. So this system exponentially grows with it is one example of. So all exponential systems, if we, for if this this is not negative, like the exponential, um, the sign of the power is not negative, but if it is positive, then obviously it is an unstable system. Now all these definitions of stability that I have given till now, they all deals with the state variables. So it talks about how the behavior of the state variables of the system. That is why so that means it is, the discussion is in the time domain. It is time domain for a given or a time domain system is expressed as differential equation form, and that can be expressed by in state space form. So you have different states of the system. What is the behavior of the system, that or what is the behavior of the states, based on that all these different definitions of stability like Lyapunov stability, asymptotic stability, exponential stability are given, and additionally you have marginal stability where it is neither stable nor unstable, and you have unstable system also, and I have given examples for each case. So asymptotic stable, so again just to repeat what I have told, is with zero input the states of the system. So important thing is it is zero input, the states converge to the equilibrium point, say xe, states converge to xe, or it could be 0 if the states equilibrium point is 0, uh, as time tends to infinity. So again I have given example. If we have xt, if there is some initial condition and there is no input given to the system from x0, it has to come back to 0. That is the equilibrium point for this system. It has to eventually exponentially come back to 0, and a typical example is, or the solution of such a system, solution of state of such a system is exponential, like e to the power minus lambda t. So you can see that it has to be negative, then only it will come back to 0. So this is the definition of asymptotic stability, and you can understand that as time progresses, so the value of this lambda t at t equal to 0, this is actually 1. As time increases, its value decreases and it goes to say 0.98, 0.9, 0.8, like this. It eventually goes to 0 as time tends to infinity, right? So this is asymptotic stability, and we understand that the state, so if the state variable is written in this form, that xt equal to initial condition into some factor, then the value of the factor should go to 0 or very close to 0 as time increases to infinity. So that basically tells you that it is asymptotically stable. Now the point from which we started, like we have understood the numerical methods, and we have to understand whether a numerical method for a given time step it is stable or not. So the basic thing that we are discussing is for a stable system, like for an example, this x dot is equal to say x dot equal to lambda x, and this system is stable for lambda less than 0, right? The system x dot equal to lambda x is actually stable for lambda less than 0 and is unstable for lambda greater than 0. So for this is unstable, and for this is stable. So say we are expressing this system, say x dot equal to lambda x with certain numerical methods, then the numerical methods should not lead to instability just because of the time step or something that we have chosen. So that is the way we will be evaluating the stability of the numerical methods. So let us start, like numerical method. You know that although continuous time system, say x dot or dx dt is equal to lambda t, then xt is equal to x0 into e to the power lambda t. So for stability you should have lambda less than 0, right? So yt, or sorry, x 0, as time tends to infinity. That is the stability that we have already discussed. In continuous time, it will look like this. X0, it is reducing. This is xt, this is time. Now for discrete time, you will not solve for all the time values, but you will solve for say some initial instance, say t0, then you will solve for t1, t2, like this tk plus 1. So for in discrete time, you will not solve for all the time instance, but your solution will only be valid, or you will be doing some solution only at some time instance, say tn, where n is from. So n is equal to 0 indicates the initial condition, and the later on L values will be 1, 2, 3, 4, always some integer values. Now let us try to evaluate stability criteria for the numerical method. So let us start with forward Euler. What was our system? It was dx dt is equal to lambda x. Now if it is solved using forward Euler, it is xn minus xn divided by h is equal to lambda of xn. If it is written, xn plus 1 is equal to xn plus lambda into h into xn. Now it can be written in this form, 1 plus lambda h into xn. So x of n plus 1 is equal to 1 plus lambda h into xn. Right? So this is the form where xn, so for the initial condition, say if x of 0 is equal, x of 0 is the initial condition, say capital X0, then xn, or basically x1, is x0 times 1 plus lambda h. x2 is equal to x1 times 1 plus lambda h, that is nothing but x0 into 1 plus lambda h square. So like this, the x1, x2, x3, x4, x5 dot 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 tending to infinity can be obtained. So if it has to be stable, it has to be, so the modulus of, so the amplitude of this thing, this multiple, or the or this factor, this 1 plus lambda h, that has to be less than 0. So the modulus, I am taking modulus because for certain cases the lambda could be complex as well, for those for like if you have exponentially decaying but sinusoidally varying things, like if you have damping in your this marginally stable this system, then additionally you will have some e to the power lambda t, and if it can be expressed as some exponential of some real term and imaginary term. So in general this lambda could be imaginary as well, that is why I am taking the exponent, I am taking the modulus of that, and this thing should be less than 1. Now if it is less than 1, then this tells us that it should be between these ones. Now let us evaluate these two things, inequalities, separately. First one is minus 1 less than 1 plus lambda h. If this is taken like this, so lambda h is greater than minus 2. So if we multiply both sides by minus, so minus of lambda into h is less than 2, and actually you can understand that for this system to be stable, the value of lambda has to be, or the real part of lambda has to be a negative number. So that is why I am taking minus of lambda as a positive quantity. So this tells us that h has to be less than 2 by minus of lambda. So the step size has to be 2 by lambda 2 by lambda or the mod of lambda. So lambda, what is lambda? Lambda is nothing but the reciprocal of our the reciprocal of time constant. So if it is a system with only one time constant, then lambda is nothing but 1 by time constant. So this equation tells us that lambda has to be at least lambda has to be lower than 2 time constants. So lambda, so h has to be lower than 2 times the time constant of the system. If it is more than that, if our h value is actually more than uh, the 2 times the time constant of the system, then even if our actual system is stable, because of discretization and taking the response of the system, it will go to instability. We will also see this in the MATLAB Simulink by solving that for different step sizes. But let us evaluate the other inequality also. Other inequality is lambda h should be less than 1. So lambda h is less than 0. So irrespective of whether it is positive negative, it is basically h is less than 0. So h is less than 0 means it is negative step size, but there is nothing as such a negative step size. So step size always has to be positive. So this part of the inequality does not make any physical sense. So for forward Euler, for the solution to be stable, the criteria is h, the step size, has to be lower than, now it is time constant of a single time constant system. If it could be multiple time constants, so there could be multiple time constants in our system also, we have to take the fastest time constant, uh, that is the time constant whose value is minimum. We have to take that and t minimum. So h has to be lower than 2 times the minimum time constant. This is only for stability. But if we want to go for accuracy, then our h has to be lower than, h has to be at least 1/10 of the minimum time constant. This is required for accuracy. Alright. So this is for forward Euler. Now similarly, let us try to do it for backward Euler also. Dx dt is equal to lambda x. If we do it for backward Euler, then n plus 1 minus xn divided by h is equal to lambda xn plus 1. Now xn plus 1 minus lambda xn plus 1 is equal to lambda h will also be there, that is equal to xn. So x of n plus 1 is equal to 1 by 1 minus lambda h into xn. So in this case the factor is 1 by 1 minus lambda h, right? In this case it is so in the same format where the future instant state value as a factor of the present instant state value, it is the factor is 1 by 1 minus lambda h. So similar to the previous case, it could be complex also. So if we take 1 minus 1 by 1 by 1 minus lambda h mod less than 1, then 1 minus lambda h mod has to be greater than 1. So either if it is positive, whole thing is positive, then it has to be this, or if it is negative then minus of 1 minus lambda h should actually be greater than 1. Now this tells us that minus of lambda h is actually greater than 0, that means h is greater than 0. So it tells us that for any no matter how small the h value is, for any value of time step, if we use backward Euler method, it will not at least go into instability, it will remain stable. I am not evaluating this second part of the inequality because it will lead to again negative value of h, which is not a physical solution. So in this case, for backward Euler we find that for any value of step size which is positive, and as it could be as high as possible as well, the system never really goes into instability, right? Now let us evaluate it for the trapezoidal also. So we have dx dt is equal to lambda x. For trapezoidal it will be minus xn divided by h is equal to lambda into half of xn plus 1 plus xn, right? So xn plus 1 minus xn is equal to lambda h by 2 into xn plus 1 plus lambda h by 2 into xn. So if we take common 1 minus lambda h by 2, that is multiplied by 1, and this will be 1 plus lambda h by 2 multiplied by xn. So our xn plus 1 is equal to 1 plus lambda h by 2 divided by 1 minus lambda h by 2 is the factor multiplied by xn. Again similarly, this modulus of 1 plus lambda h by 2 divided by 1 minus lambda h by 2, this has to be less than 1 for stability, right? It has to be less than 1 for stability. So 1 plus lambda h by 2, it's always positive no matter what, so has to be less than mod of 1 minus lambda h by 2, right? So let us take this case, let us assume it to be positive only. Now we have lambda h by 2 less than minus lambda h by 2. If we take them in the same side, we have lambda h uh, less than 0, and if we consider the negative sign of that, and it will become greater than, so h is actually greater than 0. For in this case also, for any value of step size, because trapezoidal also is a implicit solution, n plus 1 exists on both sides of the solution. So we saw that we saw from these examples that for any implicit method like backward Euler or trapezoidal, for any positive value of step size, the system is actually stable. Unlike the first most simplest case, which is forward Euler, in this case the system at least has to be, the step size has to be lower than 2 times the minimum time constant, but for accuracy it has to be at least 1/10 of the minimum time constant. Now let us take an example of a stiff system. Stiff system is mostly what we will be dealing with, like that is a DC motor or a motor drive system. Now let us understand what do we mean by stiff system. So a stiff system, so say a system, first let us consider a system which has multiple time constants. The system will be called a stiff system if there is large difference between the time constants of the system. Say a few time constants, so tau 1, tau 2, the electrical time constants for a system, for an example of the motor drive, can be few, say 10 millisecond. Electrical time constant may be as small as 10 millisecond. But say some other time constants at tau 3, that is mechanical time constant, that could be as high as say 2 seconds. So you can see that in this system you have say you have two sets of time constants. One set is quite low and another set is quite high. So you have, so such systems are termed as stiff system. So in this case, in the case of a stiff system, if you want to solve the entire system, if you want to use forward Euler, what does it tell you? It has to be forward Euler method tells you that the time step has to be at least less than 2 times the fastest time constant, that is T min. In this case it is 10 millisecond. So H has to be less than 20 millisecond, that is from the stability criteria. But you understand that this time constant, if you give some disturbance, this will very quickly die down to 0, any disturbance in the electrical circuit, because the time constant is so small. But mechanical time constant, because it's quite big, so it will take longer time to settle, and for a long time of that there will be no significant change in the electrical time constant. Of course the speed will be coming back as back EMF, and that will be disturbing the electrical thing also, but it will not disturb the electrical thing much. So if we want to simulate a stiff system using forward Euler method, then you will have to go to very low time constants, which may lead to, because your mechanical time constant is 2 seconds, so at least 10 seconds will be required for any disturbance to settle down. So say you take here less than 20 millisecond, you take say 10 millisecond, and you have to simulate the system for say 20 second. Now what will be the number of points for which it has to solve? It will be 20 seconds divided by 10 milliseconds. So it will be 20,000 divided by 10, that is 2000 points. For 2000 points the solver has to run and solve it. But for majority part of that, this smaller time constant will not matter much. So for such systems, for stiff systems, if you use a forward Euler method, then unnecessarily you will be using too much of computation, but it will not help much. But instead, if you use a backward Euler or trapezoidal method, which are uh, implicit in nature, even if you use a higher time step, say higher than 10 milliseconds, say even if you use say 100 millisecond, or say even for accuracy you will need to go for say 50, or whatever, you have to take a lower time constant at least equal to the electrical time constant. Even if, but the point is, even if you increase the time step, it will not, at least the system will not go into instability. So that is the impact, that tells you that you have to evaluate a system, the time constants of the system. If you want to use forward Euler, you have to use your time constant which is lower than at least 10 times or 1/10 of the slowest time constant. But if you have a stiff system such a motor drive system, where you have electrical dynamics, mechanical dynamics, one is slow, one is fast, in those cases it is better to go with backward Euler method of integration, which is implicit in nature. So little bit for one computation, forward Euler will be fast, and backward Euler will be slow. But forward Euler, you have to reduce the time steps to very small values in order to maintain stability. But for backward Euler, you need not reduce your time constant to such low values. So it is better to go with backward Euler method of integration for such a system. So yeah, so maybe next class I'll start with MATLAB, again the same DC machine model, and I'll show you the impact of the step sizes. That will serve as the a brief recapitulation also. And after that, till now we have studied about different uh, different this mathematical models. First we saw the differential equation model, then we saw the state space model, and then we saw the discrete, that is difference equation model. So these two are continuous time, this is discrete time, but all three are time domain. First two being continuous time and the last one being discrete time. In discrete time we saw numerical methods, which will be also useful if you want to implement your controller in digital domain, then you have to write the discrete domain different equations. So for that it is useful. And when you are going to use some numerical methods and step size, you should know what is the step size and what is the good numerical method to choose, and how MATLAB or some solver is actually solving them. So it is good to know about those things. So that is why I have discussed these things. Next we will go to transfer function model. That is the fourth representation of mathematical models. But unlike these three, where these are time domain, the fourth one is actually frequency domain. Linear time invariant systems. So it is only valid for LTI systems. It is not valid for non-linear or linear time variant systems. But we will, so this is frequency domain. So we'll understand why do we need to, we already have time domain. We will discuss something about the solution of time domain, solution in time domain, and from there we will understand why do we need to go into frequency domain and what are the different advantages of that. After we realize what are the advantages of going into frequency domain, and as we derive that, then we will derive the frequency domain model, that is Laplace transform model or transfer function model of the DC machine that we have already got. We have already the differential equations. We will get the transfer function model of the DC motor, and from there we will go into the controller design and its power electronic implementation. Okay, so we'll have our next discussion tomorrow. Any question? Okay, if no question, then let us stop. Good night.